Yeah, going to look at a specific type of rates of change question, that being growth and decay. Exponential growth and decay. Growth and decay is proportional to population. Makes sense. More people you have, the more people die, more people are born. Less people you have, less people are born, less people die. Basic idea. So I could say that that rate of change, the change of population with respect to time, is equal to some constant times the population. A very simple model of growth and decay. Well, if that's true, I can come up with a formula. My pronumeral here, though, is P, not T, so I'll turn them both upside down. The T to P is 1 on Kp. So therefore T, well, K is just a constant. I can bring that out the front. 1 on K, the integral of dP on P. Well, dP on P, that's our log function. When we integrate, we'll get our log function. So we know that T is equal to 1 on K, the log of P plus a constant. So playing around with this bit, we get Kt is the log of P plus a constant. So the log of P is Kt minus C. Undo the log, we exponentialise, if that is a word. P is equal to e to the power of Kt minus C. I can use my index laws to break that up into two exponentials. The reason I do that, e to the power of minus C is just a constant, because remember C was just a constant. So rather than saying e to the minus C, I can just say, some constant times it. But as I say, you don't have to do all that calculus. That's where it comes from. So it is using our calculus, rates of change idea. We can simply say dP to T is Kp. We get that sort of differential equation. We can say, well, I know the solution to this is P is equal to some constant, I've called it A, e to the Kt. That is the solution to that particular problem. Where P is the population at any particular time, A would turn out to be the initial population, if you think about it. Because if you sub in T equals 0, you'll get e to the power of 0, which is, of course, 1. So that constant would always turn out to be the initial population. K is our growth, or if it turns out to be negative, it would be a decay constant. And T, of course, is time. All right, the growth rate per hour of a population of bacteria is 10% of the population. The initial population is 1 million. See, because bacteria, they're very tiny. But you've got 1 million of the little gooby wops, or whatever they are. Show that. So they like doing this. They say, well, show that P is equal to AE to the 0.1T is a solution. And you might be thinking, hang on, you just said we don't have to go through that whole process. And you don't. Because it's show that, I can say, well, I know that P is AE to the 0.1T. And if I differentiate that, I'll get to P to T is 0.1A e to the 0.1T. Oh, hang on, that's 0.1P. P is equal to some constant, or to P to T is some constant times the population, so therefore it solves the problem. Okay, so that's all they're doing. They're saying, show that this solves the problem that the P to T is equal to some constant times the population. So, quickest way, just differentiate it. Determine the population after 3.5 hours. What are these little bacteria doing? Okay, well, I know that when T equals 0, that population we said was 1 million, so A is 1 million. My equation now becomes P equals 1 million e to the 0.1T. It really is just a substitution question. T equals 3.5, we get 1,419,000. So after 3.5 hours, there's now 1,419,000 bacteria crawling all over you. Don't start getting itchy, okay? Don't get itchy. Let's look at another question. On an island, population in 1960 is 1,732. Problem is, the people on this island don't like each other. And in 1970, it's 1,260. They're killing each other off. Find the annual growth rate, or in this case it will turn out to be negative because it's a decay rate, assuming it is in fact proportional to population. So we're going to assume that P to T is equal to Kp, which allows us to jump straight to the solution. P is equal to some constant times e to the Kt. Let's work out the K. We know that when T equals 0, the initial population, 1,732. So A is 1,732. We know that when t equals 10, p is 1,260. This should now allow us to work out k. So 1,260 is 1,732 e to the 10k. Divide both sides by 1,732. Need to get k by itself. To undo the exponential, log both sides. So 10k is the log of 1,260 over 1,732. K will therefore be 1/10 of that, which works out to be negative 0.0318165. So to the nearest percent, that's a negative 3% growth rate or a 3% decay rate. So in how many years will that population be half of 1960? So in other words, when is P 866? I would not, in the K, be using the negative 3%. Use that exact calculator answer, store it in your memory, whatever, but don't use the approximation. Certainly when we're dealing with exponentials, that can create nice errors if we round off exponentials. So e to the kt will be a half. Kt is equal to the log of a half. T is equal to 1 on k log of a half. Those of you that do chemistry or physics recognise that? Half-life formula for radioactive decay. Same formula basically, you just change the k depending on what you're talking about. Because that's what we're basically doing. How many years will the population be half? We're finding the half-life of this population. So subbing in the k that we found before, 21.786. So 22 years. There we go.